Okay, welcome back, everybody. I feel like it's been a long time since I've made a video. Um, so we've finally wrapped up triple integrals and double integrals and all these other wonderful things. Um, and really, that's kind of the end of, I guess, what I would maybe call Calc 3. So some colleges call it Calc 3. So what we're gonna start now, I think some places call Calc 4, which is very exciting, maybe a little bit intimidating. And the topic is going to be vector calculus, so the calculus of vectors. And to kick things off, I want to introduce you to something called vector fields. Vector fields. Okay, so as a quick reminder of things that we've talked about in the past. Long ago, we talked about VVFs. You'll remember those are vector valued functions. The idea here was that you took a number, and that was your input, right? T is our input here, and our output was some kind of a vector. It could have been a two-dimensional vector, a three-dimensional vector. Mathematically, we say that R is a map going from the real numbers to Rn, so n-dimensional, and it goes from a one-dimensional number, one-dimensional scalar, to an n-dimensional vector. The example that I have here is a 3D vector, right? Okay, so those are great. We did a lot of very fun math with them. Then we started talking about multivariable functions, MVFs, and these were just the opposite, right? These took a bunch of variables, or a vector, if you would, an n-dimensional vector, and it gave you a single scalar out. It gave you a single function out. So an example would be like my input would be x, y, and z. It would be a three-dimensional vector essentially, and my output is just this scalar function, 3x squared e to the yz plus 2. Okay, so the next big thing is, as I said, vector calculus. What we're going to deal with now is functions that map a vector to another vector, usually the same dimension. We could talk about mapping a 2D vector to a 3D vector, but that starts getting really wacky. So the idea here is the following. We're going to draw what are called vector fields, and I'm going to show you many examples of this today. But the basic idea is that your input is a point, or a vector, and I guess sort of the same thing. Either a 2D or a 3D vector slash point, and your output is going to be also a 2D or 3D vector slash point. This might seem very mysterious and very kind of, well, who cares? But we have actually seen this before when we talked about the gradients a long time ago. You'll remember that the gradient always pointed in the direction where the function was increasing the most. And I'll show you an example or a picture of what's happening with the gradient at the end of this presentation. Okay, so very quickly, here's a nice example of a vector field that I found. It's out near Hawaii, which I love. You got the big island there. I don't know what all these red dots mean, but doesn't matter. But this is the idea. This is what a vector field looks like, and it should look very familiar to you if you talked about slope fields at all in BC calculus or maybe even AB calculus. The idea there was you use slope fields, right? You're given a differential equation and you just draw a bunch of like little slopes everywhere, and you can kind of see where your solutions would lie. This is a little bit different though, because so with slope fields you just drew little line segments, and those line segments were representing the slope at any point. What we're representing here though is, I mean, we've got vectors everywhere, so we've got a magnitude and we've got a direction, and so you see where these arrows are a little bit longer, that's a greater magnitude, and where they're very short, very small, like in the middle of these eddies. These eddies are these circular areas that you see. Well, hopefully you can see these, but I would say there's like one right there, and one right there, and one right there. So you see in the middle of those eddies, the water isn't spinning very fast. You kind of got this little like whirlpool type thing going on, and in the center, the water's not going quite as quickly, but on the outside, it's going much faster. And hopefully this makes sense with angular momentum and everything else. Okay. Other typical examples of these things, again, why would we care about, why am I doing this to you, why am I making things even more difficult than they've already been? Well, magnetic fields typically use vector fields to describe them, as do gravity fields and electric fields. I've got pictures of all these things here. I'm mostly drawn to the gravity field. You see that that's the second image right here, that's this one. as a gravity field. You see, obviously, everything is coming into the point of gravity, to the center of the Earth, if you will, or the center of the sun, or the black hole, or whatever you're dealing with. And you see how the arrows get longer the closer you get to the mass, and this is this is how things happen, right? If you get farther away, there's this inverse relationship between your distance and how strong the gravitational force is on you. Okay, so what's the notation look like here? We're going to use it's this bold f, f of x and y. So the bold f, of course, means it's a vector. Oftentimes, what you'll see maybe in some of the literature is someone going to put a little arrow over top of the f like this. If you want to do that in LaTeX, you would type \vec, and then in parentheses, in your curly brackets, you would type capital F, or make that bold if you prefer. Inside of there, I just like to use a bold capital F because that arrow over top always bothers me. But do whatever you like. So again, what we're doing here is that our vector field, which I'm denoting by capital F here, it takes in two variables, x and y, or if you want to think of it as x, y, the xy vector. It spits out another vector. So vector in, vector out. And in this case, since we've only got two variables, mathematically we would say that f is a map from R2 to R2. And similarly, we could do this in 3 dimensions and map from R3 to R3. Okay, so let's talk about how we would draw one of these things. So I'd like to sketch a 2D vector field given that the field is described by f of x, y is given by the vector negative y comma x. So again, what this means is you give me any point, 2 comma 3 for instance, and what you're going to get out, what you're going to have at the point 2 comma 3 is the vector negative 3 comma 2, right? Just plug in your x and y in the right places. So what I've done here is I've given you a table of values. I'm just using the values 1, 0, and negative 1 in every possible combination, just to kind of see what's happening, and hopefully you are seeing here that you're just plugging in your x and your y. This first line, for instance, 1, 1, is giving me an output of the vector negative 1, 1. So let me just kind of draw a rough sketch of what's happening here for you. So this is saying that at the point 1 comma 1, which I believe is right there, we would start at that point right there, and then our vector is going to be the vector negative 1, 1. So that means we're going left 1 unit and up 1 unit. So my first vector is going to look something like this. Okay, it's going to start at the point 1, 1, and it is pointing in the direction of negative 1, 1. And I mean, it has the magnitude of square root of 2, all these things you remember from vectors forever ago, hopefully. Let's plot a few more of these. Let's do this one. So at the point 0 comma 1, that's this point right here, my vector is negative 1 comma 0. So that means I'm going 1 unit to the left and 0 units up or down. So it's going to look exactly like this, right? There's a very boring one at 0, 0. It's the 0 vector, so it's just basically that point. And let's do one more. Let's do negative 1, negative 1, which is down here. I'm doing this line right now. The vector there is 1, negative 1, so I'm going to the right 1 and down 1. So it's going to look something like this, I guess. Okay. And you could graph the rest of these, try it yourself just to have a little fun with it. It's hopefully pretty easy for you, but obviously very time consuming. So I don't want to be doing any of that. I recommend using technology as usual for these things. So I found this great resource. I feel like I know Kevin Hall for some reason, Kevin Me Hall. The name sounds very familiar to me. Anyways, if you go to that website, which I'm going to go to right now to show you what this looks like, it's a great resource for 2 dimensions. So this is what it looks like. If you pull up this website, unfortunately you have to type the vectors over here with the ij components, which I never like to do. But you see, so I typed negative yi plus xj, for instance. And you remember that I is the unit vector, it's the vector 1 comma 0, and j is the unit vector 0, 1. So this is the same thing as the vector negative y comma x. And you see, you'll notice a kind of a big difference here between what we just drew and what we've got going on here. And that's because my scale down here, hopefully you can see my scale, is at 0.1, so I've kind of like shrunk all the vectors by, by 90%. If I make that a scale of 1, then you'll see exactly what the picture that I just drew. I mean, in particular, this vector right here, right? This is the vector that I drew, kind of starting at 1, 1 and going to the left 1 and up 1. And here's another vector that I drew. It was this guy right there. But you see it starts getting really busy if you do the actual length, if you do the scale of 1. So 0.1 is usually a good scale to do. So you still get the general idea of how things are moving in this picture, but you don't have all the busyness of the arrows. Okay, cool. So why don't you all pause the video here for a moment, try drawing these vector fields by hand, and then going to the website. I'll show you how to do it at the website because I'm terrible at drawing these things by hand. But so the first one I'm calling it bold f. So f of xy is going to give you the vector 0x, and then g of xy is going to give you the vector x comma 0. Okay, what do you think is going to happen here? So take a minute or two, try this out on your own. I'm going to go over here. So the first one was x comma 0. So the way we would type this into this software would be xi plus, well, 0j, right? There's no j. And oh, look at that. Everything is going horizontally. Is this surprising to you? I hope not. I mean, the y component of my output, the y component of my vector is always 0, right? So I'm always going to be going to the left or to the right. And you see that, I mean, the further we get from 0, the longer these vectors are getting, the more magnitude we're getting, because it's, I mean, dependent on x, right? So what do you think the other one's going to look like if I did 0x? It would look something like this, and of course, hopefully not surprising to you, we're going to be going vertically all the time, because again, my x component is 0, so I'm not going left or right at all, I'm only going up or down. Okay, but you'll notice also that the way that the vectors get larger, right? As the x value gets larger, the vectors have greater magnitude. Okay, so this is a great way to graph these. Again, use this website. I also found a really cool, somebody made this, not me, all these formulas over here are crazy. If you look at some of these formulas, I don't even know what's going on with some of these things. I need to explore this a little bit. But I found that somebody made this wonderful vector field generator on Desmos, where you can just type in, so I've got x and 0 here right now, and that's the same vector field that we just saw. If I made this, you know, negative y, and I make this one x, then I get the other vector field that we just saw. And the reason I like this is because now I can superimpose other things on top of this, where I can't do that on the first website I showed you. So I'll share this with everybody as well. This Desmos graph. It's also very handy to draw these things. Okay, perfect. So let's look at a quick 3D example. What is this going to look like? F of xyz is given by the vector xyz. Seems pretty straightforward. So unfortunately, that website that I gave you a moment ago and Desmos only do things in 2 dimensions, which is obviously very limited. Luckily, there's a Wolfram demonstration here. Unfortunately, there's only 4 examples on this demonstration, so this one here is the one that we're interested in, f of xyz equals xyz. And hopefully it's not surprising to you that we're kind of just going away. We're sort of like, it's anti-gravity, right? We're repelling away from like the center point, which is, I guess, the origin in this case. And if you just think about this for a little bit, I mean, hopefully it makes sense, right? You're at any point, your vector is pointing at in x, y, z. It's always pointing away. It's pointing away from the origin. So that's what this one looks like. There's a few more here. Here's x, z, y, which starts getting really crazy. It starts kind of cutting in on itself all the time. Here's z, x, y, which I don't even know what's happening there. And here's negative y, negative zx, which looks also pretty wacky. And again, there's only these 4 options here because these things are probably pretty hard to generate in 3 dimensions. I'm sure there's a great applet out there somewhere that you can use for this, but this is one of the best that I could find, at least for these simple kind of linear examples that we're dealing with. Okay, so as promised, here's again kind of a refresher of what the gradient is and maybe a visual for what's happening here. So you all remember hopefully that z equals x squared plus y squared is a paraboloid. And so I've got the graph of what this actual paraboloid looks like here on the left. On the right hand side, I've got a picture of its contour map. So the red lines there, the red concentric circles, are the contour map, and I hope you all remember what those mean too. I guess the inner circle would have the least height, so that would be like a height of, I don't know, 1, and then the next circle would have a height of 2, and then 3, and then 4. And you see how the concentric circles are getting closer and closer together. the farther out you go, and so that's what's making your vectors steeper and steeper. Your vectors are always, remember, pointing, your gradient vector, I should say, is always pointing in the direction of steepest ascent, and in this case, it's just going to be pointing straight out, radially from the origin. Okay, so I hope this has been helpful for you to kind of visualize what's happening with these gradient fields. We're going to be dealing with these things a lot more in the coming videos, but definitely practice graphing these things using technology. Try them by hand a little bit, and yeah, good luck. I'll see you all soon.